now you're in really good stead, because then you just need to keep going for about 3 more weeks, and then you're guaranteed to get the capstone. If you have missed one assignment, then it's 4 more weeks. If you missed 2, then it's 5 more weeks. So it's just a bit longer, but yeah, quite a few. The juice, yeah. Juice shop is one of my favorite rooms. It's not something I picked up when I was learning, unfortunately, but it's always nice to have those kinds of very vulnerable applications that you can kind of just go ham on. So if you guys looked, I think the last task was find the scoreboard. If you looked at the amount of challenges there were in the juice shop, like you could easily spend a whole week just doing different challenges in the juice shop. And it's a great place to keep going back to throughout this virtual internship course to reinforce the concepts you practice. So like for the CSRF challenge, the assignment this week, it's not so much go and work out your own CSRF payloads as it is a guided walkthrough for many of the challenges we have you guys doing. The reason being is CSRF is itself kind of difficult. So if you, especially when you're new, it can be difficult to do. And making a payload is time consuming. So I believe there's only 1 or 2 that you actually have to make a payload for. And there's an example right before both those as well. But yeah, if you wanted to go and challenge yourself, Juice Shop may have CSRF in it. I'm not 100% sure, but there are other CSRF resources, like Portsricker has a whole bunch of labs. I'm going to give it 5 more minutes because the amount of people joining is speeding up. For Viltrum, yes, Invincible, the next episode comes out tomorrow. I am watching the series and I am enjoying it. I do not have a mustache because of it, though. Yeah. If I was as strong as a Viltrumite, though, I wouldn't complain. Ooh, there's a comment. I mean, so if you miss the first 2 assignments, you won't get removed currently. If you miss another assignment, then you would hit the 3-strike rule, and you would be removed from the internship. If you continue to complete every weekly assignment, then you'll be fine and you'll stay in the course. So just keep it up. The effort you put in over the last month, just keep that up until the end of week 12, and you'll be completely fine. So I wouldn't worry about that. Remember, if you do the best you can for 90 minutes in an assignment, you'll definitely for sure pass that thing. If you're not part of the 300, can you still go back and finish all of the questions? What do you mean the 300? Oh, do you mean the 300 and something people that I got 100% so far on all the assignments? Yeah, so like I've said before, we will close the assignment rooms, or we may close the assignment rooms at some point. I don't know if we will or when. So it's safer to play by the assumption that I will close all of the assignment rooms at the end of the capstone, because currently that's the earliest that I would do it. Play off that assumption and then be pleasantly surprised if I leave them open afterwards. Yeah, I think that's the easiest approach there. But like a good example is if we reran this course, then we can't use the same assignment rooms exactly, because there are those YouTube videos that are being made about each of the assignment rooms. So at the very least, we'll do what we've done in many of the cases and change the flags, so that you at least have to go through the effort of doing the room and performing the attack yourself to get the new flag. Yeah. Will the capstone challenge be one assignment? So the capstone challenge will be one assignment, one TryHackMe room, effectively. It's a little bit different than that, so I think we're still going to host it on TryHackMe, but you guys are going to be, probably going to use a different system for flags. But it's going to be one room. It's going to be open for the whole of the 4 weeks, and the goal is not that it's a 4-week assessment. The goal is that you have 4 weeks in which to do the assessments. It will be bigger than a single assignment. It will be smaller than 4 assignments together, right? And then there will be a separate endpoint where you go and you can submit flags. That's currently the approach, but I will have a very clear breakdown on the week leading up to the capstone and when the capstones actually happen. Yeah. I know the capstone is very interesting for you guys, and it's very interesting for me too. I like it a lot, but I'm trying to focus us on the weekly content right now and the weekly assignments. We're only on week 7, So when we get closer to like week 10 or 11, that's when we'll start discussing the capstone a little bit more. I'm already preparing you guys for the capstone. Like the best thing you could have done last week for the capstone was watch the second half of the lecture where I went and just hacked Bazaar Bank for a bit, and then went and hacked Juice Shop, because you got the weekly thing of DOM-based XSS, but then on Juice Shop, like just go and see what happens if you go and hack it yourself. And that room is still open. And there's also there's another Juice Shop room also on TryHackMe that you can go to, which has the same lab because it is a static resource. But yeah, I mean, just go and test yourself there and see what happens. Going to the virtual machine region. What region in TryHackMe are we meant to be on? So yeah, the virtual machine regions, I don't know what sounds scary. I hope it's not me. The virtual machine regions, most the time you will be fine in EU West, I think. That's normally where we do most of our work. There are some cases where the virtual machines you guys are hacking aren't in those regions, and you need to go to your settings to change the region you're sitting in. That being said, it's not, you get a warning prompt when that is the case. Most of the time, I think people's VMs start machine buttons are grayed out is probably because you already have a different virtual machine running somewhere and you just haven't closed that off. So if your start machine button for a vulnerable machine is grayed out, you should go to My Account, VM and VPN, and then see if you have any VMs running. If you do, terminate them, and then that should make your start machine button go green so you can start another one. So that's probably what the problem is there most of the time. I'm going to give it a couple more. Yes, you can keep using the rooms to practice until the capstone. They will remain open and definitely until the capstone. People are cheating out here. They barely do the assignments for just listening to the answers. No sweat of hard work. It will be fun to see the real competitors. Look, yeah, I know that some people are sharing answers and aren't doing the work and are just in it for the certificate of completion. There's nothing we can do about it. My goal here is to create the next generation of cybersecurity professionals, and I believe that can be you, right? But you need to put in the work for it. So if you're just getting the flags and completing the assignments for the sake of completing the assignments, you're not really learning anything, and like the only person you're actually teaching there is yourself. So if you're doing the work, if you're learning the different vulnerabilities, if you're understanding the root cause and the remedial actions, why the remedial actions address the root cause, that's preparing you so much better for the course itself, for career in cybersecurity, for hacking in general, than it is if you just copy and paste the flags to get the answers on TryHackMe. So yeah, people will do what people do. Keep doing your best and keep doing the best you can for learning. And as long as you yourself are learning, then I think you're in a great state. And everyone else can do whatever they want. It doesn't affect you. Awesome. I'm going to start with the slides. Yeah. Welcome to week 7 of the virtual internship, right? This week, we're going to be talking about cross-site request forgery. Now, I know last week I said cross-site scripting was one of my favorite vulnerabilities. This week, I'm not going to say cross-site request forgery is another one of my favorite vulnerabilities, but it is one of my favorite to teach, right? And the reason being is cross-site request forgery itself requires knowledge of a fairly broad amount of AppSec, like how the browser works, open cores, how cookies works, and how users interact with stuff for the vulnerability to exist. And I think it's an incredibly cool vulnerability that exists because it's more of an architecture flaw than it is an explicit vulnerability in application code. And for that reason, it's very cool to teach this, and it's very cool to watch people dive deeper and understand this. And this is the kind of vulnerability where you can understand it initially, and then you can dive a bit deeper and you can understand it more, and then you can dive even more deep, and you can just iteratively learn more and more and more about how cross-site request forgery works. So I'm excited for this one. I think it's going to be a good vuln. Please feel free to ask questions on the Discord. I was on leave last weekend, so I didn't answer as much as I generally would, but this week I will try and be more present on the Discord. So yeah, if you don't understand, do ask questions. Click. Cool. Some housekeeping. The web application that we posted last week, the vintern.thinkgreencorp.com web application that you can go and check your progress on, has been updated, so it has all of your stats and scores up until week 6. And then I know I said last week that I was gonna try and get the assignment out yesterday. Yesterday being Monday. It's too tight of a commitment. So with the turnaround of pulling in the stats from the end of last week, getting everything ready and sending it out, it ends up with the assignment only being sent out late, which I don't want to do. So the assignments will come out every Tuesday morning. That's going to be the goal for the rest of the course. So yeah, I tried for Monday. It's not feasible, so we're going to stick with Tuesday morning. I think Tuesday morning is better than Wednesday morning for you guys. The deadline is still Monday morning, so nothing's changing there. But yeah, so I did try for Monday. It can happen on it could happen on some weeks, but I can't guarantee it will happen on every week. So I'd rather go with the deadline that I can guarantee would happen every week, which is Tuesday morning. So yeah, assignments, you guys can expect them Tuesday morning as they have been and as they will be for the rest of the course. Yeah, and then last week we discussed DOM-based cross-site scripting, and then I added a whole bunch of extra spaces here, and then we spoke a little bit about how to hack. This week we're talking about cross-site request forgery, which is going to be really cool. And then next week we're finally going to tackle SQL injection, right? We're going to talk about how it works, the root cause. We're going to talk about remedial actions and mitigations, and why user input validation is not a remedial action to SQL injection, even though half the internet feels like it wants to explain to you that it is a remedial action. It is not. The remedial action is parameterized queries. Please remember that for next week. It is not input validation. It is parameterized queries. If anyone says input validation, I will go cry in a corner, I suppose. And then finally, we're going to talk about some of the more advanced versions of SQL injection. I think the basic vulnerability of SQL injection is incredibly well covered and has a lot of knowledge around it. But there's some very cool versions, out-of-band SQL injection and blind SQL injection, that we will tackle next week that actually showcase the impact and the true exploitation of the vulnerability. So we're going to go a little bit deeper than most your Medium articles will, just saying this is a payload you throw at login and then you get in. So yeah, next week will be fun, but this week's going to be even more fun because we're talking about CSRF, right? And before we talk about CSRF, we're going to take a step back for about 3 weeks. And remember SOP and CORS, right? Remember SOP is the same origin policy, meaning that browsers will only give responses to the web application of the same origin, and origin being the scheme, the domain, and the port. So HTTP localhost 80 or HTTPS localhost 443. And there were different things that were allowed and disallowed from the same origin policy. But one of the problems we had with the same origin policy was that it broke design. So the important thing here was if there was a request from admin.bank.com to the server of bank.com, because they were separate origins, the browser wouldn't send the response back to admin.bank.com. It would just discard it. And that's going to be important for us to remember for cross-site request forgery going forward. And then there was a way we could fix this with the cross-origin resource sharing policy, right? CORS, which is a set of HTTP headers designed to relax the same origin policy. And these headers are used by servers to define what content they are happy to share with who, right? So CORS is a thing, but it's important to remember by default, the same origin policy is what our browsers enforce. And remember that this is a browser level control, meaning the browsers are what's enforcing the security control, nothing else. So if you're doing a request from your terminal, you're not going to have the same origin policy apply as if it were a browser, right? And then we can relax the same origin policy with CORS. Yeah, and then here's an example of all the different headers that we can use to relax the policy. It allows origins, methods, headers, and credentials so that you can read authenticated responses. So just keep that in the back of your mind. We'll touch on that in a bit as we jump into cross-site request forgery. So, okay, never mind. There was one more slide that I forgot about. But basically what this thing is trying to say here is because we have done access control allow origin admin.bank.com, and the origin we have here is admin.bank.com. you can see that our request from admin.bank.com to the bank.com server, because our cross-origin resource sharing policy allows this origin of admin.bank.com, the request is not discarded by the browser and is sent through to the DOM for admin.bank.com. So this is a way to fix architectures that the same origin policy breaks, and is a way to share resources between two different origins, right? And two different origins, cross-origin resource sharing, right? It's all in the name. Okay, now CSRF. Okay, so cross-site request forgery, right? This is a vulnerability that it's not coded into the application. It's not like SQL injection where you're concatenating user input into SQL queries. It's not like cross-site scripting where you're concatenating the user input directly into the HTML of the page. This is a vulnerability that exists because browsers trust requests too much, right? I would say personally the root cause of cross-site request forgery is that you have a fully definable HTTP request outside of the cookie-based session identifier, right? So CSRF is one of those vulnerabilities where there are a few requirements that need to be met for the vulnerability to be present and exploitable. So the first one is the application needs to make use of cookie-based authentication. So your session identifier must be stored in a cookie and only in a cookie. The reason being is as we discussed a few weeks ago, it is the default behavior of cookies by the browser. Sorry, it's the default behavior of the browser to attach all cookies associated with the domain when sending a request to that domain. So if we go back to, if I have a cookie on bank.com, the default behavior of my browser is that when I make a request from my browser, from any domain to bank.com, it will attach all of the cookies for bank.com in that request, right? And that default behavior is required for cross-site request forgery, right? Because in a nutshell, what we're doing here is cross-site request forgery happens when a user goes to a malicious application or clicks a malicious link, and then that application sends a request on behalf of the user without the user knowing. Because these cookies are automatically attached by the browser, sorry, lost my train of thought there for a second. Anyway, so this malicious domain is sending a request on behalf of the user without the user knowing, right? Because the cookies are automatically attached by the browser. If the user is logged into bank.com and evil.com is sending a request to bank.com from the user's browser will automatically attach those cookies to the request that's being sent. So if you have a fully definable HTTP request, meaning if you can define every single part of the HTTP request except the cookies used for authentication, because those are automatically attached, when the request is sent to bank.com, you can execute actions on behalf of the user. But remember, these actions are coming from the right. So that's important to remember. So the reason it's important to remember that these requests are not coming from bank.com, but they're coming from evil.com, is when the response comes back from bank.com as to the outcome of the request, whether it was successful or unsuccessful, it would come back to a different origin, or it would come back to an origin that has not been allowed, meaning the same origin would prevent the application of evil.com from reading the response of its requests. For that reason, requests must be state changing, right? A state changing request is a request that performs some action or changes the state of some object or variable within the application, right? Most of the time, state changing requests are post requests, right? Because the variables for state changing should be in the body of the post request. Not all the time. It's not a hard and fast rule. It's just more of a process tradition. I can't remember the exact word right now that developers adhere to. It's going to bug me. But it's the way it normally happens. It's not the way it always happens. So a state changing request can be sent in any way, shape, or form. It can be sent as the parameters of a GET request. It can be sent in a POST request. It can definitely be a delete request. It can be anything you want it to be. But because you cannot read the response from the request that is sent through a cross-site request forgery attack, then you don't have any data. You don't have any knowledge of if it succeeded or not. So the only thing you can do is you can perform actions. You can't get data back. And then the last very important thing about cross-site request forgery is that when this attack, the automatically attaching your cookies to your request, right? Of evil.com does not have any knowledge of the user's session identifier in a cross-site request forgery attack. That's incredibly important to remember, because a common misconception with this is because you have the ability to perform authenticated actions as a victim, you must have knowledge of their session identifiers. But that's not the case. In cross-site request forgery specifically, because we're relying on the default behavior of a browser to attach cookies to a request for their domain, we never have knowledge of those cookies. So we're not compromising the user session. We're abusing the trust between the browser and requests, and the behavior of the browser attaching cookies to those requests when they're sent to a domain to perform state changing requests on the behalf of the user. Are you confused? That's okay. I'm going to go through this quite a few times today because I understand this is a complicated topic. I'm probably even going to bring up Paint, and I'm going to share my screen with Paint and walk you guys through this attack. So if you didn't understand that the first time, that's okay. Try and pick out different pieces that you understood there. So some of the really important parts here is one, it has to be using cookie-based authentication. Two, it's the default behavior of the browser to attach cookies to requests of the domain the cookie is associated with. And three, requests must be state changing. And four, because in a cross-site request forgery attack, by default, you cannot read the responses of your requests. And then you can add there because of the same origin policy. But remember those four things as a start, and we're going to get into a diagram as to how this attack happens. And I'm going to re-explain the whole thing. But you see how there's so many different elements at play here in this kind of attack, which is why this is only coming up in week 7. It also ties in a whole bunch of the previous weeks we had where we talked about SOP and cause, talked about the DOM, we talked about cookies, and we talked about how HTTP requests work. So there's a lot of breadth of knowledge here, and this is why building your knowledge in the previous weeks is going to support you here. And if you feel like there's a gap when you're dealing with cross-site request forgery, like you're struggling to understand how the browser attaches cookies or how cookies themselves, time to go back to the previous weeks, do a bit more research, and try and understand how that works. Okay, so we have a diagram, right? In our diagram, we have our victim, right? We have our attacker, and we have bank.com, because every single cybersecurity example ever is going to make use of bank.com and attacker.com, right? So the first step here, which is an incredibly important step, is the victim logs into their bank account, right? Why is this the first step? Why is this so important? Well, because the browser automatically attaches cookies associated with the domain, for the request to be authenticated, you yourself have to have authenticated to the web application already, right? Cross-site request forgery isn't doing the authentication on your behalf. It doesn't gain access to your cookies. It doesn't somehow magically know what your credentials are. But the first step here is you log into your bank account and you receive a session identifier in the form of a cookie, right? So then once we've logged into our account, step 3 is our attacker, the evil guy over here, and you know he's evil because he's wearing a hoodie. He sends a link to a forged request looking like a legitimate email from the bank to our victim, right? Basically, what needs to happen here is our victim needs to send the request that has been defined by the attacker, right? So that could be a request to change the victim's password. It could change their email address. It could make a transfer to the attacker. It could do anything there. But the request itself, the actions performed by the request, has been defined by the attacker, right? So when the victim clicks the link, they open the domain, or they just click the link and it sends it on their behalf, they unknowingly send the forged request to the bank. The forged request is the request that was defined by our attacker here. So this request in step 3, he sends a link for the victim to click, and then once the victim clicks the link, it sends the request that the attacker defined. Step 4 is the victim sending that request to the bank. So remember, step 4 is coming from the victim's browser. And because the victim, it's sending it to bank.com, and we have a session token or a session identifier associated with bank.com, the victim's browser is going to automatically attach their session identifier to this request to bank.com. And then bank.com will receive an authenticated request from the user asking for some action to be executed, some state changing action, and will perform that action on their behalf, which is effectively the action that the attacker wanted, right? Then, if I had to take this to a step 6, the bank.com would technically then send a response back to the victim saying that the request was successful, but the victim's browser, because of the same origin policy, would discard that request and not send it back to the attacker's domain. And that's cross-site request forgery. Does everyone understand? I'm going to actually stop here and look at the comments for a sec, the questions for a sec. So phishing is generally involved in the way where you need to get the user to click a link or to visit a malicious domain, right? One of those two things need to happen. And normally if they're visiting a malicious domain, you need them to click something. You need user interaction for other security controls that exist around cross-site request forgery. So phishing is involved. It's not required though, I would say. Okay, so cross-site request forgery, one of the requirements for it, sorry, I'm answering the question of please explain why CSRF only affects apps using cookie-based authentication again. So one of the requirements for cross-site request forgery is the fact that the application needs to be making use of cookie-based authentication. Now remember, there are two types of authentication. We've got cookies and we've got tokens, right? By default, tokens need to be managed by your front end and back end. The browser doesn't automatically attach tokens to requests to a domain, right? Your document object model or your JavaScript has to have the logic to attach that for authenticated requests. Cookies are different. Cookies were there first, I suppose, but cookies are not trusted by the browser, but they're stored in the browser. And the browser, the default behavior of all browsers is to automatically attach cookies associated with the specific domain in all requests to that domain. So if you ever set up an application that makes use of cookie-based authentication, you never have to deal with any extra logic of attaching the cookies to the requests because the browser handles that for you. Whereas with JWTs, you do have to have that extra logic in your front end because that's not handled by the browser. CSRF, cross-site request forgery, targets the behavior in cookies where the browser will automatically attach them, and it forces you to send a request to bank.com, a request defined by the attacker without your knowledge, and then it relies on the browser's default behavior of attaching the cookies for the request to be authenticated, because otherwise, who cares, right? Authenticated, it doesn't mean anything because the bank will just disregard it because it's not authenticated. It's not associated with my account. And the reason we don't care about that is because we know HTTP from week 2 and week 1 is a stateless protocol. So the only way you can associate HTTP requests with a specific person or user is through a session identifier. So if they're just randomly sending requests from our browser, it doesn't matter unless the session identifier is there. But because cookies are automatically attached, when this request is sent, the session identifier will be there. Cool. Any other questions? Sorry, I'm just giving a quick skim of what the questions are here. So one thing, the point of cross-site request forgery is to perform actions as the victim, right? So it depends on the application you're targeting, but it can be to make a transfer into your account. It can be to change their password so you can log in as them. It can be maybe to add items to a cart and purchase it and then send it to your address if you're doing, I suppose, Takealot shopping. It depends on the application you're targeting, but effectively the point of cross-site request forgery is to perform actions as the victim without needing to know what their session identifier is or their credentials. All you need for CSRF to work, if the application is vulnerable, is for the victim to click a link or visit your website, and then you automatically send that without the victim ever seeing. That's the point of CSRF. If exploitable, it's an incredibly high-risk vulnerability, but this is a 30, 40-year-old vulnerability. There's so many mitigations in place that it becomes incredibly difficult to actually exploit it. Cool. I am going to jump on over to Paint because I think some people are still a little bit confused. So give me 1 second while I open up Paint. It may be that I just really enjoyed using Paint to explain something a couple of weeks ago, and I just want to find opportunities to do it again. That may be the case. I'll never admit to that being the case, but it could be. Cool. Share window Paint. Let me bring it on the screen so I don't do that again. Okay, so we have Paint. This is the bucket, right? Cool. So we have Paint. So if we think about it, right, we have, this is a server. This is a terrible picture of a server. This is bank. And this is going to be attacker. The pictures are getting worse. I do apologize. Okay. So this is going to be attacker.com. Now we're going to have me over here. And I am on my, this is going to be my laptop, right? I'm just making it this big so you guys can see. Can you guys see? Let me zoom in a little bit more. There we go. I hope that's big enough. Let me actually just check my spare screen. Okay, so step 1, I'm just going to divide this. So this is bank. Step 1, I authenticate to bank.com, right? So the first thing I do is I log in. Right, and bank.com sends me back cookies. Right, that's cookies. That's my session identifier, right? This is what I would attach to requests to prove that is me performing a request. So if I wanted to make a payment to bank.com, I'm actually going to go a bit down here. I would have a payment, and then alongside the payment, I would attach a cookie, right? And this cookie says it's me. Right, that's basically what the cookie is. It's like this cookie proves my identity. So this is the cookie here. This is what I'm going to be referring to as a session identifier. So at this point on our browser, let's say we use Chrome, right? So on our browser, we have opened bank.com, right? And I have a cookie associated with bank.com in my browser's storage cache, right? So that's just step 1. Step 1, all we've done is expected stuff. We've logged into bank.com. We have a cookie. It's our session identifier for bank.com, right? Then attacker here, let's give him some devil horns. Attacker here sends me a request. Sends me a request saying free cookies. Oh, that's actually just going to confuse people. I'm going to say free milk because I have cookies and I want some milk with it. Anyway, so the attacker basically is sending me something to get me to their website, right? So my user then clicks. I click the link in attacker.com and I get taken to the attacker's website, right? So all that's happened here, all that's happened so far, nothing complicated. Step one, I've logged into bank.com. Step two, an attacker sent me an email advertising some free milk. And I clicked on their link and I've gone to attacker.com. Nothing malicious has happened right now. This is all normal behavior on a web application, right? Now we're going to start with the malicious stuff, right? So here, so in this case, these are two different tabs, right? So this is the tab on the right here. This is the tab for bank.com. On the left here, this is the tab for attacker.com, right? So it's not two different browsers or anything. It's just two different tabs in the same browser. Attacker.com, from this tab, so effectively from the document object model associated with the origin of attacker.com, right, is going to send a request to bank.com. Now, I'm going to pause here for a second. The request that attacker.com is sending is coming from the victim's browser, right? It's not coming from their server. The server's here. There's no communication happening here. It's coming from the victim's browser. Now, we know the default behavior on my browser is that I attach cookies, sent cookies associated with the domain to that domain. So because in step one, I got a cookie of my session identifier for bank.com, when attacker.com is making my request to bank.com, my browser will automatically attach the cookie, right? This is being done by the browser. So I would say Chrome is automatically attaching the cookie, right? This is not the attacker's website. This is not the attacker's DOM or anything like that. It's Chrome that's automatically attaching the cookie. And let's say that this request being made is a payment request, right? So it's a payment to the attacker's account from my account. So bank.com here is going to receive my payment request with my session identifier. It's going to go, firstly, it's going to check my session identifier, step one. It's going to go, this is a valid session identifier, and it's associated with Jono. Step two, it's going to look at the payment request. It's going to say, this is a valid payment request, and Jono wants to pay attacker.com, right? We see no problems, right? So there's a problem, and then my browser sees none, right? There are no problems here. So then it executes the payment, and the browser will then pay the attacker, right? So what happened here? Oh, sorry. And then the last step is it will then send a response back to me. So the bank will send the response back to me, saying 200 successful payment, well done. We'll go to attacker.com. However, Chrome will see that and it will block it. It will say, sorry, attacker.com, your origin is not bank.com. You don't get the request, and then the request will get blocked. So the attacker.com is never reading the response from my request because Chrome here is blocking it. So Chrome is like, no. You can't see this response here. It's the same origin policy as being applied to bank.com. You're a different origin, no responses for you. But because the same origin policy only applies to responses, it allowed the request through, and because it's default behavior of the browser to attach cookies, the cookie was attached for an authenticated request. So basically what happened here, I logged in, step one. I went to a malicious website, step two. The website sent a request on my behalf, step three. Step four is the browser, by its default behavior, attached the session identifier associated with my identity to that request. The bank, seeing a valid request and a valid session identifier, processed it on my behalf, and then executed the payment to the attacker's account. That's all that happened. Very simple, I hope. Does that make sense? I lost your free cookies. Okay, we're going to go over this one again. How do I clear the page? File, new. There we go. Okay, so The attack, okay. Okay, cool. I think people are understanding a bit better, but I'm gonna go through this one more time before I go back to the slides. I think I lost people on the free milk and cookies, and I apologize for that. So I'm gonna take a different approach here. Okay, step one, we have our server here, right? Server. I'm gonna call this bank. Right. Step two, we have a very big server for the attacker. Right? These are servers, right? I'm just doing a line between them so you guys can see that they're different things. But I'm going to undo that line. Then I am here, right? With my very, very big laptop. It has a lot of RAM. I bought it many years ago, but when RAM was still affordable. On this laptop, my screen, I have Chrome on. Right? And then I'm just going to divide my screen in half, right? Because we're going to use 2 tabs, right? So step one, right? The tab on the right is going to be for bank.com, right? I'm Googling, I go on over to bank.com, I request a login, right? And I give my creds. And then the bank checks my creds, the valid credentials, it logs me in. It returns a cookie to me, right? This cookie is a session identifier, right? So basically, if I attach this cookie to the request, to any requests, it associates the request with my user, and it's how the bank knows it's me performing the requests. It's because HTTP is stateless, but I'm not going to go into that now. We're focusing only on CSRF right now. So step one, I've logged in and I have a cookie, right? So here is a cookie, right? Step two, I'm on my email or something like that. I'm Googling. I'm on a random site and I make a request. So I'm actually just going to do another thing around here, just to like the edge of my browser. So my browser makes a request to attacker.com, right? This request can be like get slash, right? Just get the page. And attacker.com is like, oh great, you wanna go to my page. And it sends back the page and loads in attacker.com, right? So the attacker.com page itself is just, it can be anything. It doesn't matter what it's displaying to me. It has a hidden payload in it, right? The payload itself is a form that auto submits to create a valid request for bank.com, right? So the payload, I'm going to say form, and then we're going to do pay. So you can think of this basically, it's going to be like post, and then like my account number, value, like the amount of money I want to send, and then where I want to send it. So this is just like a normal payment request that's changed into a form, and then it's hidden in the front-end code of attacker.com. So I don't see anything about this request being made, right? Now, once I load attacker.com, the DOM or the front end will see this form, right? And it will see it's an auto submit and it will go send, right? So from this DOM for the origin of attacker.com, it will send a request to bank.com, right? And this is a payment request, right? The request is for me to perform a payment to the attacker, right? Now, currently that doesn't matter because there's nothing associated with my user. However, on the way out, Chrome sees this request happening and says, oh, your request is going to bank.com. We have some cookies for bank.com. We're going to, it's our default behavior to attach cookies of a domain to all requests to that domain. So Chrome will then attach my cookie, right? And I'm just using the drawing of cookie here. And we'll attach the cookie to the request. So when bank.com receives the request, the first thing it will do is it'll check for my session identifier. So I'll check for my cookie to see if it's an authenticated request. It goes, yes, this is an authenticated request because the cookie is attached to the request. The second thing it's going to do is it's going to go through the request and be like, is this a valid request that I can process? Yes, it's a valid request I can process. And then the third thing it's going to do is it's going to process the request. So what's happened here is I have a session cookie for bank.com. While on attacker.com, that the request to bank.com to make a payment was sent, and the browser attached my session identifier to that request, making it a valid request for my user. And then bank.com sees it as a valid request, sees the session identifier, sees the payment, and then processes it and pays the attacker, right? Currently, there's no communication here between these two servers. It's all happening on the user's browser. And then the last step, right? If you've understood this so far, you're good. But the last step is that technically, because we know HTTP is a request response protocol, is that the bank.com will send back a response. The response is 200 OK. It just really wants us to know that it executed what we asked it to, and it paid the user we asked it to. However, Chrome is going to see a response coming in from the bank.com origin to the attacker.com origin, and it's going to deny it. It's going to bounce it, and it's going to say, no, you're not allowed to read the data in this request. So attacker.com can never actually read the response here. It can never read any data from bank.com. It can only perform actions on bank.com. I hope that made sense. I'm not doing this one again. Is it possible to explain the stuff using the method you're using now going forward? Terrible drawing on a blackboard. I can try. But I hope that makes sense. Much clearer, thank you. Okay, it makes sense. Fantastic. I'm going to quickly stop sharing for a second while I move back on over. I'm not saving this artwork, I'm sorry. Give me a second, just need to open PowerPoint again from current slide. There, window. Nope, that is the right sharing. Cool. Cool. So that's how a cross-site request forgery attack works, right? Effectively, what it's doing is it's forcing a victim to make a HTTP request on the attacker's behalf. Because of the browser attaching the cookie automatically, the request is made with the context or as the current user. So it's made with the session identifier that is associated with the victim. As such, it will include any session cookies or not. So it's not just session cookies. It's just that session cookies are the one we matter, well, the ones we care about. It includes all cookies for the domain. And this is because browsers automatically attach cookies to requests. Okay. When you issue a request to the browser, it consists of specific values, right? Get my profile, edit. So this is a get request where we can see, this is what I would call a state changing request because it's changing your email to test@test.com, right? And you can see it's going to bank.com and we have our session identifier here. Some of this is defined and sent by users. So this would be some input boxes you have on the page that you can edit. So like maybe you added in the value of test@test.com and then you said, I just want to change my email. And then some of this is automatically sent by the browser, right? So that's the host. So that's where it's being sent from, content type, cookies automatically attached. All of this is done by the browser after the front end sends the request or after the DOM sends the request through. Forging a request consists of taking the user-defined parameters. So we know that this is a valid request because remember, everyone has access to the application. So we know this is valid. So we take those parameters and altering them to be what we want to be, right? So rather than test@test.com, we want attacker@evil.com, a bit on the nose if you ask me. And then if we send that from the victim's browser, the browser, as we saw in the previous slide, automatically attaches this information, the host, the content type, and the cookie. And so the browser will once again automatically attach the same information, making it authenticated as the victim. Let's see. Get profile. Cross-site concept. Oh, okay. So this is just explaining the name. Okay. So cross-site, the concept comes from the fact that attacker.com is using your browser to make a request to bank.com, two different sites cross-site. And then the request forgery is the attacker is defining the request that's going to be sent, right? It's not a request that you have any input in, it's the attacker's request. And this can be done in any type of request. So here's an example with get. So here the example, the attacker is like, hey, like click this link. Remember, if anyone on the internet ever asks you to click a link, you click it because we trust everyone on the internet. That was a joke. That was a joke. Do not click links. I really hope no one's going to click a link. But yeah, so the attacker says, hey, click this link. The victim clicks the link. And then because everything here is defined as a URL parameter, as a GET request, URL parameters are parts of links. So all you need to do for this cross-site request forgery attack to occur is click a link, and then the attack will be executed. Whereas for something like you click the link on your browser, and your browser will send through the request to bank.com, attaching any of your cookies. But for something like a post request, it becomes a little bit more difficult because in a post request, you need to define the body of the request, right? Now, by default, GET request parameters are passed as part of the URL, which are also part of the link, right? So have you ever, I mean, you guys get the Teams link from me every week. That thing has 4 or 5 very long parameters in it every week. So you can see that those parameters are passed through as a link, and by clicking that, you gain access to the Teams meeting, right? So that must have the identifier of the meeting you're joining, where it's being held, and a few other things, probably a tracking cookie because it's Microsoft. But there's several parameters in there that you need to keep track of. But your GET parameters or parameters for GET request can be embedded in a link, whereas parameters for a post request cannot be embedded in a link because they're sent in the body of the request. It's also for this reason, a little bit of a side tangent here. It's also for this reason it's more secure to use post requests for passing variables to a web application, right? If you logged in with a GET request where it's get login question mark username equals password equals, A, that can be stored as a link, but B, that's also stored in your browser history and is readable as URLs by many of the interim servers it goes through. I think it's readable as URLs, but it discloses that information. Whereas post requests don't disclose that information because the variables are in the body of the request, not in the header of the request or in the link. So it's more secure to send parameters through in that manner. Sorry, just a side tangent. Back to CSRF. Yeah, but basically here, for CSRF to be executed with a post request, what you need to do is you need to get the victim to go to a website you control or a website you have the ability to execute code on. They access attacker.com, right? And like it's a CATS page. Obviously, we're going to access that. Then you can see here in the response, here's a great example of there's an image source. So you have a picture of a cat, which is going to distract us for long enough. For this form here, so form method post, we're making a post request to bank.com/transfer, right? This is a hidden request, so it's not showing up to the user. Now we're putting in 3 inputs, right? The first 2 inputs are variables. So it's the sort code and the account number. Both of these are being inputted, and then it's being submitted, and then saying document.form0 submit as a script. So basically the form is being defined up here, and then as soon as the script is processed, it will automatically submit this form. And then the victim is going to send this request of a post request to /transfer for bank.com with the variables we see here, sort code and account number, to bank.com. And then because the victim session identifier, if they are logged in, will be automatically attached, then bank.com will see it as a valid request and will process it thereof. So key points here, CSRF on GET requests is really easy. You just need a link and you need someone to click the link. CSRF on posts, you always need to create your own payloads, a page with a form or an XHR payload. One of the things you can do for CSRF is often in a request, there is a whole bunch of unnecessary information. So you want to remove down that as much information as possible. If you're on a web application and you make a request without a tracking cookie, it's not going to break the application. If you make a request without some of the information or some of the headers, often the application will still process it fine. So you always want to remove as much information as you can for a CSRF payload, just so the payload's a little bit sleeker. And then CSRF is great as part of an attack, right? So it can be CSRF to upload a file. You can do cross-site scripting to execute the CSRF. You can CSRF to execute cross-site scripting. It's a good way to get reflected cross-site scripting working. There's a whole bunch of stuff you can do there. So it's great in chains of attacks, but there's a few problems with it nowadays, right? Before I go into the problems, I'm just going to go through you guys' comments. We may run out of time for the demo today, but I would rather you guys understand this. Does document.form0 submit steal the victim's cookie, or what does it do? Okay, so a very important thing here. You never gain access to the victim's cookie. You never have knowledge of what the session identifier is. Document.forms0.submit is, if we go back, right? So if I go back, it's saying in this document, the first form, so because it's a coding language, we start counting from 0. So in the document, remember we spoke about the document object model, where it's basically a tree-based variable structure. So it's doing this document dot the forms in this document, the first form, submit that form. It's not dealing with cookies at all. It's not touching cookies. All it's doing is it's submitting the form above, and this is just how it's referenced in JavaScript. How would CSRF work in case where OTPs are used to confirm transactions? That's a good question. They wouldn't, right? Because you don't have the OTP. You're not compromising the user's MFA mechanism, right? OTPs are a great way to prevent CSRF. MFA in general is a very, very good control. Like in general, MFA is like a second factor of authentication for login and other sensitive actions is a very good control to put on stuff, especially something like a banking application. Also, in this case, if the transaction prompted MFA, it could also warn the victim that they were under attack, because they would have gotten a random MFA from their MFA prompt from their bank saying, "Hey, confirm this payment." How does one protect themselves from this when you click the link and realize, damn, it was a malicious link? We're going to get to that. I want you guys to explain CSRF first, and then I'm going to explain why this is less of a problem nowadays. I won't CSRF you guys. Is it possible to send the SQL injection through maybe through a chatbot? I don't know what you're asking. I'm just gonna move on. Trust everyone on the trust everyone on the internet. I'm glad we're on the same page. So in my previous example, the reason I brought up the mail is whatever reason it was, you went onto the attacker's website for the request to be sent, right? The mail is just the easiest example because everyone is familiar with phishing. So you maybe got phished or whatever. But the key points there to do with the email was that you, in some way, shape, or form, got onto the attacker's website that they control or have the ability to execute code on. Can you give us a high-level overview of how the process changes if you're trying to simulate the victim on your local machine? I will do that now. Passkeys. CSRF does not. That's a good question. CSRF is. Does CSRF apply to passkeys? I want to say it shouldn't. There's other things that prevent CSRF nowadays, but it shouldn't apply to passkeys because I don't think that it's the browser that automatically attaches passkeys, and often it needs user input. but I'm not 100% sure. It could be worthwhile to go and research CSRF and passkeys and see if they explicitly talk about how they prevent that. Because generally, a good thing to see is like if someone is talking about preventing a vulnerability, it means normally by default, or like it's very easy to commonly misconfigure the technology to be vulnerable to that vulnerability, because that's why they're talking about how to prevent it. How can one bypass MFA? That's a side tangent. Remind me later if we have time. How does the attacker know the payload parameters? So the attacker knows the structure of the payload because the attacker would have access to the same site, right? So like this isn't an attacker like trying to guess what the payload looks like. It's like you go on to bank.com, you go and try to make a payment yourself. You intercept that payment with Burp. You save that request and you create your payload from that, right? Burp Suite Professional literally has an ability where you right click, generates CSRF POC, and it turns any request you want into a CSRF POC. It's incredibly easy to do with the right tools. So yeah. Yes, CSRF tokens do prevent it. Can the link be reversed from the attacker to the victim? No. I mean, like if an application is vulnerable to CSRF, you could try and target the attacker yourself. You shouldn't, because that would be illegal. The most you can do from the link is you can work out what the attacker was trying to do, and maybe you could notify the application that, hey, it looks like you may be vulnerable to CSRF or something. And maybe you can try and see where the link came from, like how it was sent to you or something. But no, you couldn't. This isn't like you can ninja it back to the attacker and get them to pay you money. Okay, I'm going to move on to the defense now. Okay, so the remedial action for a CSRF is a CSRF token, right? So if we think back to the beginning, right? The very first slide I did, I said the root cause of CSRF is a fully definable HTTP request, right? So the problem here is not that you're making use of cookie-based authentication. Remember, it's incredibly important in security that we enable the technology around us, not that we prevent people from doing what they want to do. So the solution here is not to get rid of cookie-based authentication. The solution to CSRF is to make use of a CSRF token. A CSRF token is a long and random token associated with the user's current session that is sent as a hidden input field at the top of a request and response, right? Basically, the thing here is this has to be sent with all state changing requests and generally should be changed. But this is an extra layer, or this is an extra value that has to be present on a request for it to be valid. That the attacker wouldn't know about with CSRF, right? So I'm going to go back to Paint to explain this because I feel like it was easier. I shouldn't have closed it. Yeah, sorry, I'm used to teaching CSRF on a whiteboard. Paint. Let me bring that back on the screen. Okay, we're back here. So I want you guys to remember that on our webpage here. So in the request, in the example we had, it was a post request, right? And it had the variables for the account num, right? And it had the source code. Then by default, we also had the cookie attached by the browser. Now, this is where we're sitting, right? None of this can change. This is just how this stuff works. You can't remove variables from a request. You can't prevent the browser from automatically attaching cookies. This is just how all of this works, right? So the problem here is if this is valid, right, you're vulnerable to CSRF. Now, the way we prevent you from being vulnerable to CSRF is we need to add something else, right? I'm going to try and write something else. You need to add something, and that something is a CSRF token. Right? So the reason we want to add this CSRF token is that and it's incredibly important that we add this not as a cookie, right? So this CSRF token stored maybe somewhere like local storage or session storage. It's put in our requests as a hidden input field. You guys will remember in week 3, the really hard brute forcing challenge, there was an extra parameter called user token. That was a CSRF token. That's a good example of a CSRF token. It can be sent as a header. It can be sent as basically anything you want except a cookie, right? But the primary thing here is that this token has to be associated with your user session, right? So you can't just have any random token. It has to be directly associated with your user session. And when a state changing request is being performed, it has to check for the presence of this token for it to be valid. Right? And this relies on the fact that in cross-site request forgery, the attacker has no knowledge of the information from the application, right? So remember the fact that we said that the attacker doesn't actually have the ability to read the responses. Because of the same origin policy, responses back to the attacker are actually blocked, right? So the attacker can't read responses, meaning they don't have knowledge of our session identifier or our data or our CSRF token, right? The attacker, because they can't read responses, they don't know any of these things, right? They're relying on the fact that the browser is automatically attaching the cookie for a valid request. We need to add something else, right? So we need to add the CSRF token as something else that adds another factor for a request to be valid that isn't automatically attached to the request, and the attacker cannot predetermine, right? So the attacker can so if we think back, the attacker can predetermine the request structure, right? So they can predetermine the request, and the browser attaches the cookie, right? So we need a third thing, right? We need something that isn't automatically attached and isn't predetermined, and that is our token. And with this needs to be handled by the front-end logic. But with this token, if it's not present, the request is rejected because it's an invalid request. A request is only accepted if the token is present in the request. So no token, no request. And because this is not automatically attached, right? So it's not attached, and the attacker cannot have knowledge of it because it would be the same thing as a session identifier, then the attacker cannot predefine a valid request for a user to perform an action. So this does not matter, right? So a CSRF token is the remedial action for CSRF because it addresses the application at the root cause. Yes, so that if we go back to our example, remember we've got bank.com, we've got attacker.com, and we've got our browser, right? If you are on attacker.com and you send a request to bank.com, the response coming back from bank.com will get blocked by your browser because of the same origin policy, right? Bank.com and attacker.com being separate origins, it will be blocked by your browser. Also, interesting thing, with cross-origin resource sharing, you can do ACAO, access control allow origin star, which allows any origin to read responses. This by default doesn't work on authenticated responses. So if you're performing authenticated actions, it's still blocked by the same origin policy, even if you're doing ACAO star. That's a side note that doesn't matter that much. The important part here is this: the same origin policy is blocking responses from bank.com from ever reaching the document object model of attacker.com. So the attacker cannot read our responses. There is a huge wall here that's called our browser saying no. Yeah, okay, so So we now have confirmed that the attacker can't read responses from bank.com. The CSRF token, right, is effectively, it's easiest to think of it as a second session identifier, right? So what this is it's a hidden input field on your page. So you've got your cookies up here. And on this cookie, you would have your session identifier. And then maybe you'd have something like input CSRF. And then your CSRF token would be part of the body of your request, right? So this is a response, call it, right? And then the logic of our application would go and read the CSRF token and store it in our browser, not as a cookie, just as a variable. And if, say, for example, we want to make a request like change our password, this would be sent as a header or as a parameter or as part of the post body, a header, a custom header, anything but a cookie. Anything but a cookie. It cannot be a cookie. It will be sent to the web server. If the CSRF token is not present, it's not a valid request. Because the attacker cannot read responses, so they cannot read this response here, they won't ever have knowledge of our CSRF token. So they won't know what this value is. And without knowing what this value is, it becomes impossible to create a valid request, making it impossible to perform a CSRF attack. Does that make sense? This is turning into the drawings of a madman. I do apologize. Would adware serve as an effective mechanism for coercing or affecting it? Yeah. I mean, if you can if you can send a request from the ad, even like that would work. This gets it gets incredibly complicated when you start dealing with iframes and elements and stuff like that. We're just focusing on the attack right now. Okay, cool. You understand. Okay, so CSRF tokens are the remedial action, right? They fix it for that reason. Just going to quickly open this up. Yeah. Okay, we're going back to our slides. This time I haven't closed Paint because I know it's going to open again. Sorry, one sec. We're experiencing technical difficulties. Okay. There we go. Okay, so that's what I wanted to talk about. So synchronized token patterns, also known as CSRF tokens, honestly only known as CSRF tokens. I only ever use the word synchronize a token pattern when I'm teaching this stuff, is the remedial action, because it's impossible for the attacker to gain knowledge of a CSRF token through a CSRF attack to construct and if they cannot gain knowledge of the token, they cannot construct a valid request. And if they cannot construct a valid request, they cannot perform actions on behalf of the user. So CSRF tokens have to be hidden input fields or custom headers. They cannot be cookies. I have said that a lot. Why have I said that a lot, right? Well, if we think back to why a CSRF attack works. A CSRF attack works. The first requirement is it makes use of cookie-based authentication, because it is default behavior of the browser to automatically attach all cookies associated with a specific domain on all requests to that domain. What does that mean? If your CSRF token is a cookie, it is useless because it will just be attached on requests to that domain. Don't laugh, I have seen it, right? Now, there is a very niche like bypass mitigation where they try to double submit, like they submit the request twice. I've never seen it work. And I think it's covered a little bit in the assignment as well. CSRF tokens just fix it. So implement CSRF tokens. So it's incredibly important that CSRF tokens are not cookies, because if they are cookies, they're useless. They are just a session identifier. They get attached automatically and you're still vulnerable to CSRF. Right? A couple other factors on CSRF tokens. One, they need to be long and random, right? The reason they need to be long and random is because they need to be they can't be guessable, right? Because there's like the whole point is the attacker can't have knowledge of this value, right? And the user never needs to use or see the value to make it long and random, so the attacker can't guess it. Yeah, they have to be long and random. 2, they have to be associated with only your session, right? So there's no point of just checking if it's a valid CSRF token on the application, because at that point, the attacker can just log in, get their own CSRF token, chuck it over to the request and see if that works. No, it has to be specifically tied to your session, so that it doesn't open up that attack path. And then 3, and this is a little bit more defense in depth, but these tokens should be regenerated on every state changing request, right? So whenever a state changing request is implemented, the token should be checked. Okay, it's valid. And then the response should set a new token. That's less important, but the very important part is every time you log in, definitely you should have a new token, right? Now, it should also be that it's regenerated on every state changing request. But the attack surface at that point is a lot smaller than if you don't have one, right? So like it's a priority thing. It's very easy to do if you already have it implemented to just regenerate it on state changing requests. So you may as well just go and do that. But the important part is that you have a long random value for your CSRF token that's directly tied to a user session, right? And then that token is regenerated on every state changing request and is sent with every state changing request. There's no point having this token if it's not sent on a state changing request, right? Like if you can't CSRF, if the token's only sent to make transactions and update your account details, but isn't sent when you change your password, that's kind of useless because like you're changing your password. They can still get access to your account that way. And then it's always useful, like where if the CSRF token is not there, there's something wrong because your application will always send the CSRF token. So you can log out the user if it's not present or something like that. It's a nice alerting thing because like it's one of those things where a normal functioning of an application by a user would never not have the CSRF token. So if the CSRF token is not there, something's gone wrong. It's either something is broken or there's someone's being malicious. So it's always worthwhile noting. And then the second thing that actually makes this really difficult to exploit in the modern day. Firstly, CSRF is really well known. CSRF tokens are very present, and most applications are quite secure against CSRF. And a lot of web application frameworks are actually quite robust against CSRF by default. When you use the session management for these frameworks, it implements CSRF tokens without you actually having to do anything. It's just part of the session management packages that you deal with. So by default, CSRF tokens are quite omnipresent. But the second one is the same side flag on cookies, right? So the same side flag, there are 3 cookie flags. I think we've discussed these before, but it's secure, HTTP only, and same site. The secure flag cookies will only be sent on an encrypted connection, so will only ever be sent over HTTPS communications, never over HTTP. The HTTP only flag, the cookie cannot be used by JavaScript, so it's a very good mitigation for cross-site scripting to stop users, threat actors from stealing your session identifiers. The last one is the same side flag. The same side flag has 3 settings, which I did not include in the slide, so we're going off memory, right? So the 3 settings of the same side flag are strict, lax, and none. So none is vulnerable to CSRF. Basically, it means that the same side flag does nothing. Right? It's as you would expect. And then strict, I'm quickly trying to Google the values to get them right. The strict value will prevent the cookie from being sent by the browser to the target in all cross-site browsing requests. So basically what the strict value does is the cookie will never be sent in a request coming from a different origin from a different domain of the cookie's domain. So if your same site flag is set to strict, then attacker.com sending the request, that cookie will never get attached because of the same site flag being set to strict, right? However, that breaks functionality. So strict is the most secure option, but it breaks functionality. None is the least secure option, but it breaks security.
So there's a middle ground, and that middle ground is called lax, right? Same site lax is meant to be the balance between security and usability, right? So, and I go and research this yourself because there's a lot of very weird edge cases on same site lax. But as far as I remember, the same site lax flag will never send the cookie in post requests originating from a different domain than what the cookie is associated with. It's called a CSRF prone request. So it's like post, put, delete, update. Basically any request with the body, to be honest. But like any request that can perform an action, if that request originates from a different domain than what is associated with the cookie will not be attached to that request, preventing cross-site request forgery. The reason that this is actually not a remedial action in itself and only a mitigation is because it will still attach the cookie on GET requests. And I can stand to be corrected on this part, but I believe it attaches the cookie, or it also will attach the cookie on post requests. Now, this is when you get very specific on things. On post requests within the first 120 seconds of authenticating to a web application. So that's a very small attack window. And after that point, it won't attach to post requests. But the reason that this is not a remedial action is because if you do have a state changing request on a GET request, you would still be vulnerable to CSRF, which is why we abide by coding traditions and have our state changing requests be what is expected, such as post, put, delete, update, those kinds of requests. So the same site flag is a very good mitigation, and it's actually gone a huge way to reduce the presence of CSRF within the internet, but it's not a remedial action because some people don't listen to the development traditions and they still make use of GET requests for state changing requests. Also, just to add a little bit of fun there as a side tangent, right? Some web application frameworks, I'm not sure, I think it's the backend frameworks, support interchangeable GET and post requests. So your request is valid whether it's in the form of a GET request or a post request. It's all changed into the same thing and dealt with the same way. So at that point, it completely bypasses the GET and post restrictions on the same site flag, because all post requests can just be changed into GET requests and would still be valid by the backend server. So that's just a side note. It is honestly, it's a vulnerability if you allow that, but I have seen that. And it does enable cross-site request forgery. The last thing on the same site flag is you're going to need to go to MDN web docs to 100% confirm this. But the thing that makes the same site flag as effective as it is today is many modern web browsers by default set the same site flag to lax if it's not set, right? So what that means is when you get a response back from the server, you get a set-cookie value. And that has the cookie name equals value, and then it's got all the flags set on the cookie, so HTTP only, secure, and same site equals whatever. If you don't include the same site flag, it defaults it to lax, which is resilient against most forms of cross-site request forgery. I think it's every web browser except maybe Firefox. And also, it's worth noting the Burp Suite Chromium by defaults all same site flags to none, just for security testing reasons. But yeah, so default, if you don't set the same site flag, it's generally set to lax. That being said, you should still set it to lax because it's not all the time. If cookies are automatically sent by the browser, why isn't cookie-based authentication enough? Why do we need? So we need CSRF tokens on top of cookie-based authentications to prevent cross-site request forgery. And it's because cookies are automatically sent by the browser, and that's just default browser behavior. The 3 cookie flags are HTTP only, same site, and secure. I see people are beating me to it on the comments. Where is the malicious request generated by a CSRF attack sent from? The malicious, okay, so the request is sent from the victim's browser. So the attacker defines what the request looks like, they define the payload and all of that stuff. And for a post request, say, for example, they would embed a form into a page. The user visits that page, and then the victim's browser, so the person who is being targeted by this attack, sends the request. Their browser also attaches their session identifier to create a valid request, but the malicious request is technically coming from the victim's browser here. not the attacker's server. Does the tokens change? The tokens should change with every request. CSRF tokens change with every request. And it's the CSRF tokens, is not the session identifier. Is Firefox safe to use? I use Firefox. Like all browsers are going to have their own vulnerabilities. I use browsers based off what I want to do with them. So say, for example, if I don't want to have ads when I'm browsing the internet, I would use something like Brave. If I wanted something that's going to be present on all Microsoft operating systems, whether I wanted to or not, I would use Edge. If I just want to use a common browser that everyone's going to have, I would use Chrome. And then I'm sure Opera has a use case. It's not something I'm that familiar with. So there was meant to be a demo. It is, however, 7:25, so there's not going to be a demo. It's a bit late for a demo. So if you guys just ask questions, I'm going to start scrolling down and cover all the questions that I missed.